Okay, so I thought before I get into the actual subject, there was one thing about cataclysmic, about planetary nebulae and common envelope evolution, which I didn't get to mention, and it came up. I thought it would be nice since there was questions about Minkowski, and who was the one who invented type 1 and type 2 supernovae, and his uncle was the Minkowski of the Minkowski metric. But Minkowski also was the person in charge of the first Palomar sky survey, so the 48-inch Schmidt first all sky survey was done under Minkowski's guidance. And one of the things he discovered was this amazing planetary nebula. This is M29, I think this Minkowski, ninth object in Minkowski's second catalog of planetary nebulae. So this is an HST image. There's the white dwarf that's making everything shine. And this is a combination of nitrogen, oxygen, and sulfur lines. And the remarkable thing about this one, as many other planetary nebulae, is this hourglass. Right? There's something seems like holding the inner edge in, and for a long time it's been postulated that perhaps there was a binary, and as the binary spiraled in, some material was ejected from the L2 points or in the common envelope and came out in the equatorial plane, so there ought to be some disk of dense gas. And here is the beautiful ALMA image. This is blue shifted is coming towards you, red shifted going away, and there's the torus of a few 10 to the minus 3 solar masses of molecular gas, which is actually confining the hot wind of material coming out from the white dwarf. This is the zero velocity cut, so that sort of shows you what's in the plane. You can see there's an outer torus and an inner torus, and the torus is slowly expanding at about 6 or 7 kilometers a second, as you can see in the channel maps down here that sort of show you which is coming towards you and which away from you. So that gives a kinematical age of about 1,400 years, so we're pretty sure that this material was ejected 1,400 years ago. The binary is believed to have an orbital period of 90 years, so there are pictures of this nebula covering 70 years, and there's basically little spots that seem to be going back and forth on the 90-year time scale. And the radius of this molecular torus is about 2,000 AU. So we actually see the interpretation of this object is that this may be maybe something which is sort of just being stripped from the red giant companion. So if there's a nearly Roche-Lobe filling red giant that's coming into contact with the white dwarf, this is the first torus of material that's being stripped off. Yeah. Okay, so the disk is nearly edge on. Okay, but it's tilted a little bit, so the top part is coming toward this blue shifted. You can see the blue shifted material in the channel maps here. This is coming towards you, and the below is going away from you. So they've color coded the channel maps here. So there's a torus like this, which is expanding like so. You're looking at it a little bit below edge on. Okay, so just to remind you, last time we discussed what sort of causes stars to come into interaction. So as either the orbit shrinks or the star expands, first one star will fill its Roche-Lobe, the contour, the Roche equipotential contour going through the L1 point. Then one can fill both of them, then you can fill out to L2. But the reasons that we discussed last time that things can be brought into contact, either you can lose angular momentum through gravitational radiation or magnetic braking on the tidally locked stars that we discussed, or through just evolutionary expansion of the star on off the main sequence and up to giant branches. But in the last lecture on the common envelope, I sort of mentioned that there was this starting problem. And to get around the starting problem, everybody basically just puts the companion into the slowly rotating envelope and then it spirals in. And we sort of glossed over the question of when is it actually appropriate to stick the companion in the envelope and make the envelope slowly rotating. So now let's go through and actually discuss what timescales the mass transfer happens on. When is it dynamical? When is it on much longer time scales, so that you would expect to have more stable transfer. So one can do a linear stability analysis and imagine that we have, let's say, star 2 is the one which is filling its rush lobe first, and it will start to transfer its mass towards the companion star 1, going through the little nozzle at L1. I'll discuss a little more last time. One important point that sometimes is a misconception: the gravitational acceleration in the rotating frame changes sign at L1. So it goes, the gravitational acceleration is exactly 0 at L1. But everywhere else on the equipotential through L1, the gravitational acceleration is still pointing in towards this star. So when filling the rush lobe does not mean that the star spherically overflows the rush lobe. It means that the material goes through a little nozzle. There's a little tiny hole here where material starts to go through onto the other star. And material on this side of the star has to flow over the surface and get through the nozzle. So it's more that you have a little vacuum cleaner and you start sucking material off the star from this point. It's not that you're overflowing out the back, out of all sides. Okay. So material starts to flow through the L1 point, and the question of what then happens to that material: it might be ejected from the system, it might be accreted onto the other star, either directly or after making an accretion disk, which carries the angular momentum out and by tides puts it back into the companion's orbit. So there are a lot of things that might happen to the orbital angular momentum and a lot of things that might happen to the mass. It might either end up on the companion or be blown out of the system. So depending on how the mass and the angular momentum, what happens to them, that will determine how the rush lobe's size changes. Right? It will be different depending on whether angular momentum is conserved or mass is conserved. That will determine the rate of change of the size of the rush lobe. So we'll have to worry about what happens to the mass and angular momentum in order to decide how the rush lobe size changes. And then the second thing is, once I've removed a little bit of mass from star 1, the star is going to readjust in some way. It's lost some mass. So the very first thing it does is you remove some mass, the star is no longer in hydrostatic equilibrium, it has to reestablish hydrostatic equilibrium. So it expands or contracts a little bit, and that happens for the sun on a time scale of a few hours. It's a characteristic time scale to reestablish hydrostatic equilibrium. And in a few hours, the sun doesn't have time to transfer much heat anywhere inside the star, so the readjustments are basically adiabatic. You preserve the entropy of each little mass element, and you preserve its chemical composition, of course. Now, after you've readjusted, then if nothing catastrophic has happened, your star hasn't become unstable and disappeared into the other one, then you can, on a much longer time scale for the sun around 10 to the 7 years, then this star which is expanded is no longer in thermal equilibrium. Some parts will have a little too much energy and some will have too little, and the heat transport through the radiation will be reestablishing the thermal equilibrium in the star. And for example, the expansion of the core might have dropped the nuclear reactions, so the nuclear reactions are no longer supplying radiation at the level that's needed to be carried through the rest of the star. So the whole star has to readjust, but this readjustment in 10 to the 7 years is happening on a time scale much faster than the time scale to change the chemical composition through nuclear reactions, which in the sun is like 10 to the 10 years. Okay, so that readjustment is at fixed chemical composition. That's actually a little bit of a lie. If you move a convection zone, you can mix some regions which weren't previously mixed or stop mixing other ones. So that's not quite true, but there's certainly no nuclear reactions, so the total chemical composition doesn't change. And then after that readjustment time scale, finally you can wait for the whole nuclear evolution time scale, and the star will then continue its evolution, perhaps the thing which actually put it into contact in the first place of the radius expansion of going up the red giant branch. Okay, so in order to decide what happens, what the stability properties are, we have to compare the change in the radius on the dynamical time, on the thermal time scale, and on the nuclear time scale with the change in the radius due to the exchange of angular momentum and mass that determine how the rush lobe radius changes. And the mass transfer will occur on the first time scale for which the change in the radius of the star is larger than the Rush lobe radius change. Okay, so it should be obvious. If the Rush lobe is expanding and the star is shrinking, there's not going to be any continued mass transfer. But if the star is expanding faster than the Rush lobe is expanding, then the star is going to exponentially overflow its Rush lobe, and the transfer will happen increasingly rapidly, unless that large transfer then causes the star to not expand faster than the Rush lobe. Okay, so let's work out a very simple example. So let's pretend that we have a fully convective donor. So convection is very efficient in stars, except possibly in a very skinny layer near the photosphere. So a fully convective star is nearly isentropic, and if it's not radiation dominated, it's like an n equals 3/2 polytrope. And those have radius which scales as mass to the -1/3 power. Okay, so on a dynamical time scale, if I remove a little bit of mass from the star, it hydrostatically adjusts by expanding due to the mass loss. The star gets bigger. But in thermal equilibrium, a fully convective low-mass star on the main sequence has a radius proportional to the mass. Right? It's just the mass-radius relation for main sequence stars. The virial temperature is roughly set by the nuclear burning temperature, which is nearly independent of, of density. And so Gm over R is nearly constant on the lower main sequence. So on the thermal time scale, the star eventually has to shrink in response to the mass loss. Okay, so here, this shows the response on the dynamical time scale. So in hours, the star will expand if I remove a little bit of mass. But then over a time scale of a few 10⁷ years, it will shrink back down, and it will actually end up smaller than it started. Okay, so it first expands, and then on a thermal time scale, it contracts. So it's conventional to define, after webbing, to define zeta d log r d log m. So, and then one can put subscripts on this to indicate whether it was working on dynamical time scale. So one convention is to call it zeta dyne. Another convention is to call it zeta s, meaning constant entropy. But in any case, it's -1/3 in that case. And on the thermal time scale, or in thermal equilibrium, so you can choose either thermal or equilibrium as your subscript, it's just 1, r proportional to m. Okay, so now we know how the star's radius expands. Now we need to figure out about the Rush lobe. So the first stage in figuring out what happens to the Rush lobe is to figure out how the orbit size changes. So if I have two stars which are tidally locked, there's a little bit of rotational angular momentum, and there's a whole lot of orbital angular momentum. So we'll neglect the little bit of rotational angular momentum and say J is equal to L, the orbital angular momentum. And so for a star, and say a pair of stars on the semi-major axis A, you can write the semi-major axis in terms of the angular momentum, the total mass, and the mass ratio, mu, m1, m2 over the total mass. And so if, let's do the simplest possible thing, we imagine that we magically conserve both total mass and total angular momentum. So total mass conserving says that what goes off one star ends up stuck on the other one. There's no mass loss in winds. Total angular momentum is a bit more subtle. I would take mass off one star, it's carrying angular momentum with it, and that angular momentum would end up on the other star, making it spin incredibly rapidly and have a spectacular winds and braking, except that maybe you have an accretion disk, and the accretion disk carries angular momentum out until it gets so close to the mass-losing star that all the angular momentum goes back into the orbit through the tides. So that's the usual assumption. So let's pretend that the mass transfer strictly conserved both angular momentum and mass. Then if L is conserved and total mass is conserved, you can see that the only thing varying is the m1, m2. So the semi-major axis goes like 1 over m1, m2 squared. So if I differentiate that, you can write d log A is twice the mass difference divided by m1 d log m2. So if m1 equals m2, the semi-major axis doesn't change. But if, for example, the less massive star is losing the mass, then this term is negative, so the orbit is, the semi-major axis is shrinking. Okay. sorry, this term is negative, d log m2 is negative, so sorry, in that case the orbit is expanding if the less massive star loses mass, and the orbit shrinks if the more massive star loses mass. Okay, so now we've got the semi-major axis size. So if we consider the extreme case m2 much less than m1, that case is very simple to understand. Imagine that I have a satellite orbiting the Earth, and I take a little bit of mass off the Earth and I double the mass of the satellite. Take some rocks off the Earth, add them to this Hubble Space Telescope to double its mass, and I insist that total angular momentum be conserved. That means that the Hubble Space Telescope must have moved in by a factor of 4, because the angular momentum is square root of gma. I've doubled the mass, and so the semi-major axis goes like 1 over a squared. Sorry, 1 over m squared. So if I increase the mass of the satellite, it must move in. If I decrease the mass, it goes out, proportional to 1 over m squared. Okay, so a goes like 1 over m squared in that limit of the companion being much less massive than the first one. Okay, is the ratio of the Roche lobe to the semi-major axis, and that limit just goes like the mass of that body to the 1/3 power, just from the tidal equations. So zeta L d log RL d log m is an m to the minus 2 times an m to the 1/3, so that's minus 5/3. And if you keep all the algebra in, you find it's minus 5/3 plus twice the mass ratio. And the convention I'll use that most people in this business use is that Q is the ratio of the donor to the accretor. Okay, so from this equation, you can see that the Roche lobe expands if Q is less than 5/6, and it shrinks for Q greater than 5/6. But remember, for a fully convective star, the magic number was not 0, expansion or contraction, but it was minus 1/3 for the dynamical transfer. So if we equate these two, zeta equals zeta L, you find that the magic value of Q zeta L is minus 5/3 plus 2Q. You equate that to minus 1/3. So if Q is less than 2/3, then the mass transfer will be stable for a convective donor. And if Q is, if the mass ratio, if the donor is more than 2/3 of the mass, then it will be unstable. Now, if we consider let's start with a binary with two stars of unequal mass. The more massive star evolves faster. So if it's a wide binary and it makes a red giant, which is convective, and it's more massive than its companion, then generically that's dynamically unstable transfer. So the first time that we come into contact will typically be a spiral in a common envelope, because you'll have a convective star that's more massive than the companion, and that will be unstable, dynamically unstable transfer. Now, once I spiral in, what's left behind is just the core of that giant, which will be substantially less massive than the giant, so it might be more or less massive than the companion, depending on the companion. And the companion might be fully convective, or it might have a radiative envelope, or it might have a convective envelope with a radiative core, or for higher mass, even vice versa. So the second contact, sort of unlike the first one, may be either stable or unstable. And there are 3 cases to consider. One, which is the one that we already looked at, is if zeta L is greater than zeta on the dynamical time scale, then the mass transfer is unstable on the dynamical time scale. You just overflow and lose the mass over a few orbits into a common envelope. Then a slightly more interesting case is if zeta dyne is larger than zeta L, so it's dynamically stable, but it's larger than the zeta on the thermal time scale. So remember that the star readjusts on the thermal time scale. So if that produces a radius expansion which is less than the Roche lobe one, then the transfer will be stable on a dynamical time scale, but unstable on the thermal time scale after the star has time to readjust. And then finally, there's the case when the zeta for the Roche lobe is less than both of them. In that case, the transfer is stable on the dynamical time scale and the thermal time scale, And if there's going to be any mass transfer, it has to be due to angular momentum loss or stellar evolution. There's no response to the star, which is driving the mass transfer. Okay, so the little example I worked out was for sort of a n equals 3/2 polytrope, a fully convective star. Radiative stars, by contrast, are stably stratified, right? The heat transfer is carrying heat from the hot region in the center to the outside. They're stably stratified, so that means the entropy on the top is higher than the entropy on the bottom, right? Just like it is in LA when all the smog stays put. So if I now remove an outer layer of a star like that, I'm removing the highest entropy material, and that means that the star is going to shrink in dynamical response to the mass loss, unlike the isentropic polytrope, which expanded when I removed mass. So if the star is shrinking on the dynamical time scale, that means the mass transfer can be stable even for quite large values of Q. So here's just to show you, so these are basically tracks. I start with a star of mass 1, which varies from 0.3 solar masses, 0.4, 0.5, up to 1 solar mass. And this shows what happens to the radius of the star if I adiabatically remove half the mass or 80% of the mass as I shrink the mass down from 100% of its initial mass through 50%, 20%, and so on. And you see that the 0.3 solar mass stars, which are fully convective n equals 3/2 polytropes, just steadily expand as I remove the mass. That was the polytrope example I gave you. But if I take a star like the Sun, you see that the Sun has a convection zone, which is, you may be surprised, it's 20% of the radius of the Sun, or 25% of the radius of the Sun, but it's like 10 to the minus 3 of the mass. So the convection zone is 1 pixel on the screen here. Once I've removed that, then the Sun basically just shrinks as I remove mass. And then if I keep removing mass, eventually I get down to such a small core that I start to get a little bit of re-expansion, but I never even pass the initial radius, even when I have only 1/10 of the solar mass left. Okay, so radiative stars shrink, convective stars expand, and if I have a mixture of, the 0.4 or 0.5 solar mass star has a very thick convection zone, so it's sort of having trouble deciding whether it's radiative or convective. And the bottom plot just shows the entropy to show you that indeed the stars that are mostly radiative have higher entropy in the outer parts. That's why they shrink. Okay, so the radiative star on the dynamical time scale, I remove the high entropy outer layer and the star shrinks, but now heat transport is going to try to readjust and rebuild that entropy profile, so heat gets dumped into the outer layers, and that makes them expand back again. So on the dynamical time scale, the radiative star shrinks, but on the thermal time scale, it expands back. Okay, so this one is typically going to be in this limit, that it's stable on the dynamical time scale, but unstable on the thermal time scale. It shrinks in response to mass loss in the dynamical, but it expands on the thermal time scale. Okay, so typically when I have radiative stars and the mass ratio larger than about 1, so that it's unstable after it re-expands back towards its initial radius, that re-expansion will happen on the thermal time scale, and that leads to mass transfer rates of dumping significant fraction of the star on its thermal time scale. So that's mass transfer rates that are like 10 to the minus 6 solar masses a year or more for these stars. Now, 10 to the minus 6 solar masses a year, you'll remember for a neutron star, 10 to the minus 8 is the Eddington luminosity, so this will be 100 times Eddington. So neutron stars are clearly going to have trouble having conservative mass transfer at those kind of accretion rates. They're actually interesting, so this is for Lars, this is the high accretion rates when I get hydrogen shell burning and I can start to rebuild a red giant, because the white dwarf can't actually burn 10 to the minus 6 solar masses a year. And if I try to dump this onto, say, the Sun, that's increasing the Sun's mass by a factor of 2 in 1/10 of the Sun's thermal time scale, so the Sun can't readjust itself on that time scale, so the whole thing will swell up. So with these high accretion rates, the companion stars basically always have trouble. All of the companions you might be interested in have trouble accepting at that rate. So in addition to worrying about the donor, you better start worrying about the accretor in that case as well. Now, especially at these high accretion rates, if you imagine that, say you had a neutron star and you're accreting at 100 times Eddington, you might expect that 99% of the mass is going to be blown out of the system. Therefore, mass is not conserved and probably angular momentum is not conserved. And therefore, our little calculation of zeta L was wrong because we assumed mass and angular momentum conservation. So it's especially at those high accretion rates, one typically has to do much better, and it's not appropriate to consider conservative transfer. And so you can consider about winds off the giant, winds from the accretion disk, mass loss from L2, making rings around the system. And a student of mine and I went through all the possible cases we could think of, and they're all nicely programmed into Mesa. So if you want to do those cases, you can turn the switches on and off in Mesa. Okay, so that was polytropes and words. Let's look what happens if we actually take honest stellar models and actually honestly remove a little bit of mass from a fully computed stellar model. So this sort of shows the bottom curve here is the main sequence, and the top curve here is the base of the giant branch, and these are models sort of evolving from the main sequence up through the giant branch, so the stars are somewhat different structure as they go up here. If you look down in the lower main sequence below, say, half a solar mass, you see that the magical Q, so this basically is a way of specifying zeta adiabatic, assuming conservative transfer, then the magic value was 2/3, and this reproduces 0.7. Okay, so the analytic worked pretty well. But if you look up here for the radiative stars, you see that the magical values of Q are sort of in the range of 2 and 3. Okay, so that was the statement that you could have quite high values of Q be stable for radiative stars because they're tending to shrink on mass loss rather than expand. And you'll notice that funny things start happening here, like the 80 solar mass star is acting like a convective n equals 3 halves polytrope. You shouldn't believe that part of the diagram, I think. Okay, just one fun thing that can happen. If I have a radiative star and I look at what happens to the star the track of the star as I vary its mass. So this red curve shows the adiabatic stellar response. So that's just how the radius of the star changes in response to the mass loss. So this is its mass divided by its initial mass. It starts here, and as I remove mass, it's a radiative star, so it shrinks. Okay, but remember, if I can conservatively lose mass, and I'm losing it from the more massive star, then as I lose mass, the Roche lobe is actually shrinking. So the question is the Roche lobe shrinking faster, or is the star shrinking faster? If the Roche lobe shrinks faster, then it's going to be unstable transfer. So if you look at when I first start losing mass, the star is always shrinking faster than the Roche lobe. That's because the outer parts of the star have quite a steep entropy gradient, so they shrink very rapidly. But as I keep removing mass, if the mass ratio were, say, 3, so the star that's losing mass is initially 3 times more massive than its companion, then it's always dynamically stable. But if the mass ratio is 3.757, then after I've lost about 1/3 of the mass, suddenly now I'm starting to have the Roche radius shrink at the same rate as the star. And if I go to a somewhat higher Q, like 4.5, initially everything's stable, but at this point, now the star is not shrinking as rapidly as the Roche lobe, and at this point I go dynamically unstable. So in this case, I have a phase of thermal transfer, a thermal timescale mass transfer, until I've lost about 20% of the star, and then it goes dynamically unstable and makes a common envelope. And that's delayed dynamical instability. Okay, so now let's discuss what happens to the material that's lost in the case when I'm transferring either on a thermal or a evolutionary or angular momentum loss timescale. So, as I said, the Roche contour here, all this material is still nicely bound with a finite gravity pointing in everywhere except at L1. And so matter gets sucked out of L1, and you might think, oh, well, it's just going to fall onto this star. But no, remember the Coriolis is in a rotating reference frame. So when the velocity is, radial velocity is 0, it just keeps going round in circles. But as soon as it starts to develop an acceleration and a finite velocity in this direction, then Coriolis force deflects the orbit in the rotating reference frame. So the material actually spirals around and intersects itself. Okay, so the stream comes off L1, it gets deflected. If it was the very first stream, it comes around, it intersects itself, there's a spectacular shock, a collision, you heat stuff up, and then the material starts, the next material that comes in hits the ring of material that's from the collision, and I gradually start to build an accretion disk, and then viscosity starts to spread the disk. Okay, so then the disk moves outwards towards the L1 point until the tidal interaction between the companion star and the outer edge of the disk transfers mass from the outer edge to the companion, just like the gaps in Saturn's rings and so on, exactly the same phenomenon. Okay, so you'd like to figure out how much does the star have to swell beyond the Roche radius in order to supply material, and as it swells beyond, how does the mass transfer rate depend on the swelling radius? And it's sort of easy to work out to order of magnitude and very difficult to do anything better than order of magnitude, that the accretion rate goes like the density of the portion of the star at L1 times the sound speed there cubed times the r cubed over gm characteristic timescale. And you can see that as the star swells up, this mass transfer rate is going to go up extremely rapidly, right? If I get the photosphere of the star and then I go a little bit more, the density is going up exponentially. And then as I start to get past the photosphere, then the sound speed starts to go up as well. And so this mass transfer rate is going to rise spectacularly rapidly as I start to overflow the Roche lobe. So if my transfer is on the thermal or a nuclear time scale, I only need a very small accretion rate in order to be transferring the star on a thermal or dynamical timescale. And that means I need only a very slight extension beyond the Roche lobe in order to get the accretion rate to balance the mass loss rate. So it's nearly a good approximation to say that the star is just always filling its Roche lobe. It's actually always slightly overfilling it. But from the point of view of understanding the mass transfer rate, you don't really have to worry about that. So the two pieces, so you can then work out the actual mass transfer rate. So it'll depend on 1 over the difference of these two zetas, which goes to infinity as I approach the stability limit. And then there are two pieces, each of which you compute at constant stellar mass, so ignoring the mass transfer. One of them is the rate of change of the Roche lobe with respect to time. So this would be 0 if I didn't have any angular momentum angular momentum loss in the system. And if I did, then this term might be the important term. And this term is just d log r dt at fixed mass, so this is just the evolutionary rate of growth of the star. Okay, so the case that I want to talk about for the rest of the lecture is the case of an initially wide system with a nice massive star, say 1 to 30 solar masses, and a little low mass star as the companion. So the first transfer, when I get this incredibly massive red giant and this little low mass star, that's spectacularly dynamically unstable. Okay, so I get a common envelope and I begin to spiral in, and the low mass star spirals in around the core of the other star, and the envelope, as we saw, gets ejected in the planetary nebula. And we end up with a much tighter orbit after the spiral in with a low mass star and the core of this giant, which might be a white dwarf or a neutron star or a black hole, depending on the mass of the initial star. And this transfer now, if this star is, say, 0.6 to 1.4 to more if it's a black hole, and this is a little 0.3 to 0.6 solar mass star. When this star, say due to angular momentum loss, eventually fills its rush lobe, this phase of transfer is going to be stable. Okay. So we want to look at that final phase. It only got that close because of dynamically unstable evolution, but the phase we're looking at is now going to be stable transfer. Okay, so the first thing to do is to look at a whole bunch of these observed systems that have low transfer rates, so they're not spectacularly losing mass on a dynamical timescale. And we'd like to check the theory that I just described, namely, do these systems actually have mass ratios such that they ought to be transferring not on a dynamical or thermal timescale? So here's the calculation. Here's the critical Q for dynamical timescale evolution, and the critical Q for thermal timescale evolution in red. And here are all the cataclysmic variables known to have modest accretion rates that are not on the thermal or dynamical timescale. And you see that, yes, they are all stable, theoretically. Okay, so that part of the theory seems to work. And now let's look what happens to the accretion. Okay, so the three cases to consider, I said there could be a white dwarf, a neutron star, or a black hole. So let's start with the white dwarfs. The white dwarfs that are accreting are traditionally called cataclysmic variables. That might give you the idea that they have outbursts, cataclysms. And the cataclysms that I will talk about are the disk and instability in the accretion disk. Exactly these same systems, as more and more material piles up on the surface, they can have thermonuclear explosions, and Lars will talk about that in subsequent lectures. So the accretion disk instabilities come in various varieties, named, as astronomers love to do, after the prototype, which often is not actually a member of the class to which it becomes the prototype after careful study. So there are papers entitled, Is SU UMA and SU UMA? So SU UMA's systems have so-called normal outbursts interspersed by much bigger and longer outbursts called super outbursts. The U Geminorum systems supposedly just have the normal ones, but of course U Geminorum after 20 years finally did have a super outburst, so U Geminorum is no longer a U Geminorum system, but is now an SU UMA system, not to confuse anybody. And then there are the Z Lepardalis, whatever it is, the 12th variable star in the giraffe. And those have outbursts followed by a plateau where they remain at constant luminosity for days or years and then drop down again. All of these systems, the accreting star is a ordinary low-mass main sequence star, mostly made of hydrogen. There are similar systems where the companion is a helium star, for example, a helium dwarf in a very short orbit. So the helium white dwarf is now filling its rush lobe and accreting material onto a carbon-oxygen white dwarf, and those are called AMCVN systems. And they do pretty much the same thing, but shorter orbital periods and different time scales, but exactly the same sorts of instabilities. So there's an interesting correlation, which is if you look at the amplitude and magnitudes, so astronomers measure these in amplitudes and magnitudes, it sort of says 2 to 5 magnitudes. But there's an interesting correlation that the amplitude of the variability correlates with the time between the outbursts. So the longer you have to wait between the outbursts, the bigger the amplitude. So it's as if you have to wait for a certain amount of fuel to accumulate in the disk, and the longer you accumulate fuel, then the bigger the outburst. So this is called the Kukarkin-Parinago relationship. So far I've been talking basically about white dwarfs where the magnetic field is unimportant. I will mention in the next slide and thereafter not say anything more about there's a whole collection of white dwarfs with strong enough magnetic fields to either prevent the accretion disk from reaching the surface of the star by cutting out a hole where the magnetic pressure is comparable to the ram pressure in the accretion disk, and then the extreme highly magnetized cases where the magnetosphere extends basically out to the L1 point and the material never forms an accretion disk at all, but just gets funneled in along a field line into the magnetic pole. And these are called intermediate polars and polars. There are also, the examples I was talking about were basically with the main sequence companion. There's similar systems where I have a white dwarf accreting from a red giant companion dominated by nuclear evolution rather than angular momentum loss. Those have higher transfer rates, and because of that, usually no disk instability. And those are called symbiotic stars because you see the spectrum of the red giant and the spectrum of the white dwarf, so you can tell they're two stars. In the cataclysmic variables, usually the accretion disk is much brighter than the little pathetic low mass companion star, so you just see the spectrum of the disk. There are perhaps some supersoft sources, and single degenerate type 1As are basically systems of that source with the red giant accreting onto the white dwarf. Okay, now if we replace the white dwarf by a neutron star, those are low mass X-ray binaries at rather low accretion rates. Low mass X-ray binaries at high accretion rates don't display these sorts of gigantic outbursts, but at low accretion rates they're called soft X-ray transients, and that should give you the idea that the X-ray luminosity changes enormously. And there are also neutron star analogs of the AN CVNs with helium donors, and those are called ultra-compact X-ray binaries because to accrete from a helium white dwarf, you need a very short orbital period so the little white dwarf can fill its rush lobe. So there are shorter orbital periods in the systems with hydrogen donors. But again, just like in the AM CVNs and the white dwarf case, they show exactly the same kinds of accretion disk instabilities as the hydrogen systems do, but again, at shorter orbital times and shorter recurrence times. So here's an example of a low mass X-ray transient. So this is 3 years of MAXI data, and you will notice that this source in 3 years had 3 spikes. The next one wasn't actually bigger. It didn't keep going to infinity. The peak luminosity, so this is Aquila X1. It has roughly 1 outburst per year for the past 40 years. The peak luminosity is around 10 to the 37 ergs a second. The quiescent luminosity down here is around 10 to the 33. So the luminosity at peak is roughly 4 orders of magnitude larger than the quiescent luminosity. This really is a spectacular outburst. And how do we know this is a neutron star and not a black hole? It's because in addition to having these kind of outbursts, it also has thermonuclear bursts, the so-called type 1 X-ray bursts, which happen when you burn fuel on the surface of a neutron star and there's no surface for a black hole to burn. So we're sure this must be a neutron star. So this is actually one of the more pathetic X-ray peak luminosities. It's only 10 to the 37 ergs a second, but this is also the most rapidly repeating one. And for these low mass X-ray transients, there's an analog of the Kucharkin-Paranago relationship, which basically says that things that repeat rapidly have lower peak luminosities, and ones that have only 1 outburst every 10 years or every 30 years have much higher peak luminosities of 10 to the 38 ergs a second and up. So here's just another, I just randomly picked a Swift source of the X-ray outburst, just to show you that this one triggered during the initial few seconds of the burst. This was, the neutron star was so hot that it actually triggered the Swift gamma ray detector. And then over a time scale of tens of seconds, it rapidly faded, and here it continued going for 10 days. So the average luminosity averaged over the 10 days was around 10 to the 36 ergs a second. The peak luminosity was a few 10 to the 38, and the quiescent is undetectable at less than 10 to the 32 ergs a second. So this one had a 6 order of magnitude jump in X-ray luminosity between peak, and even averaged over 10 days, it was more than 4 orders of magnitude. Accreting black holes with low mass companions and low accretion rates are called soft X-ray transients. Here's a collection of them. The first and maybe most famous one was AO620-00. It's known from Harvard plate stacks to have had an outburst in 1917 but the one that got it noticed was 1975, because then there were X-ray satellites, and the X-ray luminosity went up, and then it came down over the subsequent 6 months. Then it's currently somewhere down here, but it's been rising over the last 3 years, so it's probably going to have another outburst sometime in the next decade or two. So the X-ray luminosity in this case rose by more than a factor of 1,000,000 above the quiescent. And here are a bunch of other ones, and you can see they all have roughly the same light curves. And crudely in the Milky Way, there's one new one of these every year discovered. And they have recurrence. I mean, the ones we know about that have recurred have recurrence times of less than 50 years. The ones which have only gone once maybe have recurrence times of hundreds or thousands of years. We don't, but we think they probably all recur on some time scale. Now, this course we decided to emphasize optical transients, but these sources actually are also optical transients. So the upper curve in each of these cases is the optical magnitude shown on this side, and the lower curve is the X-ray flux, the counts shown on this side with factors of 10 each major tick mark. And so you can see that, for example, AO620, during the X-ray outburst, the optical jumped by 6 magnitudes. So that counts as a spectacular transient. It's rather entertaining. This was Kulker's noticed that if you plot, let's see, I think in black is AO620's optical light curve, and the squares are a light curve of a system AL comb, which is a member of the WZ Sagitti class, but the name I like better are toads, which means totally overwhelming. Let's see, what was the word for this one? Yeah, it was totally overwhelming accretion disk outbursts, CVs. So, and you notice that the light curve even has a little dip in the same place, similar amplitude, 7 magnitudes of change in flux. Probably a coincidence, but maybe there's some deep meaning in the accretion disk outburst. But. Okay, now in addition, so I mentioned that there's this big jump of 5 or 6 orders of magnitude in the X-ray luminosity between quiescence and the outburst, but there's all kinds of interesting stuff that happens in the top 1/1000th of the X-ray luminosity, transitions between different states as it goes across towards the soft state, and the luminosity drops between a 10th and 100th of Eddington. The sources typically get relativistic radio jets coming out of them, sort of just like in AGN. And then as it drops down below about 1,000th, then the jets tend to turn off. The spectrum of the source changes. There's a whole phenomenology of quasi-periodic oscillations and spectral changes which occur around this cycle. But again, this isn't about X-ray variability, so I won't say too much about that. Okay, so now the theory. So we have our companion. We have the stream from L1. The disk is now expanded out until tides are truncating the outer edge of the disk. So the stream is now hitting the outer edge of the disk. There's a hot spot, which you can actually see as the orbit goes round. You see the little hot spot where the stream intersects the disk. And then there's the accretion disk with the white dwarf and its boundary layer in the middle. So there is a single elegant theory for all of those objects, that diversity of objects I've been telling you about. It covers the dwarf novae, the cataclysmics, low mass X-ray transients, black hole X-ray transients, hydrogen disks, and there's a very similar theory for the helium systems, just with different ionization and different temperature. So let's consider the hydrogen case. So basically, the model, which does remarkably well at explaining all of these systems, is that I will get these kind of gigantic outbursts if the outer edge of the accretion disk has a temperature which is less than 6,000 degrees. If the outer edge of the accretion disk is hotter than that, there are no such outbursts observed. And why is 6,000 degrees special? Well, that's roughly the temperature at which hydrogen recombines. And sorry, you'll have to look at these here. So this is my little plot of the opacity. And you notice this red color, the opacity is 10 to the 4. Here the red is 10 to the 4. And the green is opacities of a few centimeters squared per gram. So there's a tremendous dip by about a factor of 1,000 in the opacity as I go through about 6,000 or 7,000 degrees Kelvin. Okay, so that huge change in the opacity as I go through 6,000, 7,000 degrees means that the disk has two choices of state. Either it has a cold, low opacity state or a hot, high opacity state. And as I'll show, what happens because of that, as I pass through that region where the temperature is around 6,000 or 7,000 degrees, the stable solutions for the accretion disk are either a much lower accretion rate than the rest of the disk or a much higher one, but there is no solution with an accretion rate which matches the rest of the accretion disk. So there is no steady state disk for a disk which goes through a region where the temperature is 6,000 or 7,000 degrees. So there's no steady state disk, so what the disk does is it then cycles between the low state, which is stable, and the high state, which is stable, but it can never find a stable solution, so it just oscillates between the high state and the low state, and that's what produces the outbursts. And in the high state, everything's being funneled through much faster than it takes to refill in the low state with a low viscosity, so the outbursts are much shorter than the quiescent phases. Okay, so let's see how that works in a little more detail. So just a review of accretion disks. So if I'm orbiting a point mass, the velocity goes like 1 over square root of r, so the closer I am, the faster I'm going. That means if I look in a little local region here, I have material that's moving faster next to material that's moving slower. So there is a frictional coupling between the two. And that frictional coupling, first it removes angular momentum from A and gives it to B. And B gains angular momentum, A loses angular momentum. But if I'm in Keplerian orbits and I lose angular momentum, that means I get closer. And if I gain angular momentum, I can move farther away. So A moves in and B moves out if I have frictional coupling. And the other thing that happens if I have frictional coupling is I generate heat. So heat gets generated in the accretion disk. Now, the viscosity, people talk about it as if it were viscosity, but it's not actually molecular viscosity. The Reynolds number in typical accretion disks is 10 to the 10 or 10 to the 15 or something. But certainly in these hot disks and the X-ray binaries and cataclysmic variables, the material is sufficiently ionized that it's highly conductive. And the famous MRI, magnetorotational instability, says that even if I start off with some incredibly weak magnetic field, the magnetic field will exponentiate on an orbital time scale until it develops to a level where it gets saturated by the magnetic forces becoming comparable to the shear forces, and so it has a back reaction on the shear, and the magnetic field can start to reconnect or rise buoyantly out of the disk. And when it saturates, the magnetic pressure is somewhere between a few hundredths and a tenth of the total pressure in the system. So this is just a recent simulation by Shi and Jim Stone and others. They considered a big box. So this side of the box is showing density, and on this side it's showing the energy in the magnetic field. And there are 3 simulations here, 32 cells per scale height, 64 and 128. And you're supposed to be impressed that 32 looks different, but 64 and 128 are pretty similar. That means that they think they've numerically converged. And the quantity plotted here is the magnetic stress divided by the total pressure. And you see that it's saturating at some value like 0.08 or 0.1. So that was the statement that I gave you, that the magnetic pressure, the magnetic stress is around a tenth of the total pressure. This was an unstratified shearing box, which is kind of unrealistic. Had no net magnetic flux, which probably arguably is realistic for some cases. If you do stratified boxes, you discover that the magnetic field starts to get generated and it rises out buoyantly, and so the disk gets magnetic cycles just like the sun's magnetic cycle, where it develops a strong field and then it rises out buoyantly and then it grows another field, and there are periodic changes in the magnetic field. And the average magnetic stress is a bit lower than in this case by a factor of a few, but it's basically the same idea. Okay, so taking those simulations at face value, we'll now proceed to write down the equations for our accretion disk. So the first thing is the angular velocity. It's just the Keplerian angular velocity, because if we assume that it's a thin disk, so the cooling is efficient and is able to balance the heating, then there's negligible radial pressure support, and so the material must be nearly Keplerian. Then the viscous stress, the brilliant idea first of Shakura and Sunyaev, and now finally sort of verified by MRI simulations, is that the viscous stress is some alpha times the pressure, where alpha, as I just showed you, is some number like 0.02 to 0.1. And we can write that as nu times omega k, remembering viscous stress is the viscosity times the gradient of velocity, which has units like the Keplerian angular velocity. So I can rewrite this to say that the viscosity is the same dimensionless alpha times the sound speed times the scale height. So that's sort of what you might have guessed if you put a mean free path equal to scale height and estimated a viscosity. So then I can write down the viscous torques in the disk that I described. The faster moving material exerts a viscous torque on the slower moving material outside. And conservation of mass and angular momentum with the viscous torques gives you this equation, which you recognize as the time derivative of the surface density is a d by dr of a d by dr of something. So this is like a diffusion equation. So the surface density of the disk diffuses on a viscous time scale with the velocity that's given by this equation. So if I start, for example, with a ring of material, it will gradually diffuse out, mass moving in, a little bit of material to conserve angular momentum moving out, and the ring will gradually spread at a rate given by this, determined by the viscosity. Okay, and likewise we have a mass conservation. If there are no disk winds, you can forget about this term and you just conserve the mass. And in steady state, one important equation to remember is that nu times the surface density is just basically m dot over 3 pi as long as I'm far away from the inner edge of the disk. Okay, so that was radial structure. Now what about the vertical structure in the accretion disk? And here's where the opacity comes in. So the vertical structure, of course, it has to be in vertical hydrostatic equilibrium, and the vertical gravity is basically just the h over r piece of the radial acceleration. So the radial acceleration is balanced by the Keplerian motion, but that can't balance the slight vertical tilt to the direction of motion. So there's a omega k squared z is basically gm over r squared times z over r, so it's the vertical component of the radial force, and that has to be balanced by dp dz, the vertical pressure gradient. So that's the hydrostatic equilibrium, and now I have to have a heating balancing cooling. So the heating is being set by the viscosity, and remember I said that sigma nu is basically just m dot over 3 pi, so the heating rate is just determined by m dot times gm over r cubed. And that sometimes you can write as sigma t effective to the fourth, just like you do in stars. So this gives the heating per unit area. And then if I want my disk to be in thermal equilibrium, then I have to balance this heating with the cooling. And if we don't worry about convection, that depends on where I do the heating and vertically in the disk, which we don't actually know yet, even from the simulations. Let's just say it's radiative, then the vertical flux is just given by, just like in stars, the gradient of the radiation pressure. And so I can write this as the sigma times the central temperature divided by, here's the part of the place where the opacity comes in. Okay, so remember, in this narrow range between, say, 5,000 and 10,000 degrees, the opacity dips by a factor of 10 to the 4 and then climbs back up again. So this flux is incredibly sensitive to the value of this temperature and the opacity there. And then I need an equation of state. Okay, so those equations, it's a whole nasty nonlinear coupled system. So you go ahead and solve it. So here's just calculating that vertical structure with realistic opacities as a function of temperature. for a disk that's accreting 10 to the minus 9 solar masses a year around a sort of heavy white dwarf or light neutron star at a radius of 10 to the 9 centimeters, so nice, well within the Rush lobe and outside the white dwarf or neutron star radius. And you find that the thermal equilibrium curve, the equilibrium you get by solving those equations that I wrote down, follows this S curve. So along this solid line, the heating rate equals the cooling rate. If I go anywhere off this solid line, on this side, the heating rate is larger than the cooling rate, and on this side, the heating rate is less than the cooling rate. Okay. So let's consider I perturb myself off here. So if I go up here, now the heating rate is larger than the cooling rate, so I'm going to cool back down again. This is temperature. Okay, if I go down here, now the heating rate is larger than the cooling rate, so I go back up. So this side is stable. You can do the same argument here. This is stable. But if I go here and I perturb myself up a little bit in temperature, now the heating rate is larger than the cooling rate, so I just keep going up. And if I perturb myself down here, now the heating rate's less than the cooling, so I just keep cooling and I go down. So this branch here is an unstable branch. And you notice that that unstable branch is basically between 5,000 and 7,000 degrees Kelvin, where that hydrogen ionization instability was. Okay, so what actually happens if I consider a little ring of material like this and I perturb it? Well, what actually happens is that the ring, if I perturb off, it goes up to this hot branch. And now there's a nice stable solution, so it follows down along here until it gets to this point. And now there's no stable solution anymore. So it drops down to the cool branch. Now it finds a stable solution, so material gradually piles up until it gets to here. Now there's no stable solution, so it goes in a limit cycle like this, switching between the hot state and the cold state. And in this cold state, remember it's a very thin, very cold disk, so the viscous timescale becomes extremely long, so it moves up here very slowly. Then in the hot state, there's very high pressure, very thick disk, so enormous viscosity, so the material dumps very quickly. So there's a rapid movement here and then a slow climb back up. So in this state, you'll notice that everywhere in the disk is below about 5,000 or 6,000 degrees, whereas in this state, it's hotter. So that was a single ring. But of course, that little ring, once it decides to get into this high state and be transferring much more material than it was previously, that's going to affect the rings of material on either side of it. So I can't just consider one little ring in the disk going up and down, varying its mass flux through it, because that's going to affect the neighbors. So we have to do a global calculation. So here's a global calculation. So what happened in this case is that I had an accretion disk, which was starting off in the state where I was building material up, gradually supplying material, and the disk was cold and thin, and everywhere was below 7,000 degrees. And at this point, around a little less than 10 to the 10 centimeters, was the place where the disk first reached a temperature of 7,000 degrees. And at that point, it suddenly decided to make its transition. It no longer had a stable solution here, so it made a transition to the upper branch, just at that one little point in the ring. And now this thermal front then starts moving out. So there's a very high accretion rate, so material inside, so material starts to flow out of the disk. And as this thermal front moves out, it basically heats up the rings outside so that they also get above 7,000 degrees and begin to enter the high state. And in this case, the thermal front actually got to the outer edge of the disk, and that means that the whole disk was now transferred into the hot state, and the whole disk rapidly accreted. So this would be a case in which we make what the CV community would call a super outburst. That's the best you can do. You dump all the material in the disk into the star, making into the white dwarf, making a giant outburst. Depending on the amplitude of this perturbation and the structure and outer radius of the disk, it can happen that sometimes this front dies before it gets to the outer edge of the disk, and then you only dump a small part of the disk, and that would be normal outburst. Okay, so I should say that this idea of disk instability as a way of explaining CVs was first proposed by Osaki in 1974 and then developed considerably by Meyer and Meyer-Hofmeister in 1981. And the first application to the black hole case was by Minishige and Wheeler in 1989, and there's a whole huge literature on, on this subject by now. Okay, so that was sort of what this was sort of up through the outburst. Now that I've dumped the disk, what happens after that? So the inner part of the disk in the high state is now producing a huge amount of radiation that heats the outer part of the disk and keeps it in the high state for a while. And then once the self-irradiation, once I start draining the inner disk, then the outer parts of the accretion disk cool rapidly back down to the low state and the system enters quiescence. A rather sad feature, I would say, of these models is that that actually doesn't work if you just do it as I described. You actually have to say that the inner part of the accretion disk at some critical accretion rate magically turns off, maybe because it becomes an advection-dominated radiatively inefficient disk. That would be plausible for the black holes, not so plausible for the neutron stars, and very implausible for the white dwarfs, but you still need to do it in order to reproduce the observations. So it's a little bit of an embarrassment to try to get the sudden drops at the end. Okay, so what about models versus the observations? So I would say the greatest success of this model is basically that almost every system which has a temperature at the outer edge of the disk of less than 6,000 degrees is observed to have these type of bursts, and systems with temperatures at the outer edge of the disk higher than that don't show bursts. So that, I think, is a gigantic hint that ionization instability has very much to do with the outbursts. Those who spend lots of time in this business can explain almost all the features of the light curves by adjusting the alpha parameter in the high state, the alpha parameter in the low state, the triggering radius, the irradiation, the shape of the disk, the evacuated central region. You have 5 or 6 parameters. You can adjust them and you can produce light curves that will match the data. I would say it's not extremely predictive of the light curves. There are some features of them which are, you can sort of, for example, lower accretion rates give weaker and faster bursts. It's sort of a generic prediction, and that sort of gives you the Kucharkin-Paranago relations I mentioned. But you know, I think we don't have any very good theoretical reason for these differences in the alphas, and certainly for dropping out holes in the inner parts of the disk, except maybe in the black hole X-ray binaries with the ADAFs and so on. So you know, I think probably the physical idea is correct, I think, but it's not something where one can a priori predict every detail of the light curve just given an accretion rate. I'll just mention one thing, sort of a lead in to Lars's lecture, that for a long time there was a question, these same systems which undergo these outbursts in the cataclysmic variables, after they've built up enough material that's been accreted through the accretion disk, having these accretion disk cycles, eventually they build up enough material that there's a nova eruption, a thermonuclear burning occurs on the surface of the white dwarf, blows off a huge amount of mass, tremendous luminosity, and there were suspicions that maybe that nova explosion could actually change the properties of the companion, either the companion star or perturb the companion's orbit, and so that the actual supplied accretion rate might be different before and after a nova outburst. And that was never actually verified, although people since Paczynski in the 1960s had proposed hibernation models for novae, that after a nova outburst the cataclysmic variable phase would cease. But in 2009, Nova Centauri 2009 V1213 Cyn had a nova eruption, and this system had been observed for 6 years reliably beforehand, and it had nice little outbursts of the disk accretion instability type that I mentioned. But since the nova outburst, and the 6 years after the nova outburst, the source has steadily been 6 times brighter than it was beforehand than average, and it's never shown any CV outbursts since then. So it's clear that the rate of mass supply from the companion was increased substantially by something that happened during the nova explosion, and the system now is hot enough at the outer edge of the disk that it no longer in steady state has CV outbursts. Okay, so I think that's all that I wanted to say about these, so I'll open it up for questions.